Let's welcome Barry Smith. He's going to be speaking today on defining intelligence. Welcome, Barry.
Okay, so this is a talk which it was co-authored by myself and Jobst, who is online and who will be engaging with me and with the audience towards the end of the talk, if that turns out to be needed. So there is a little bit of mathematics at the very end of the talk, and Jobst certainly is more competent than I am to talk about those aspects of the proposals that we are going to be defending here. So Jobst is a member of a quite prominent German family, the family of the Landgräbers. His grandfather was Husserl's last assistant and somebody who was quite influential in the phenomenological world in Germany. Jobst himself studied in Göttingen, and he worked in these institutions on topics which are directly relevant to the topic that we're going to be dealing with today, which is human intelligence and the relationship between human intelligence and brains and biology more generally. Jobst actually knows something about artificial intelligence, which is the main topic of this talk, since he founded a company devoted to using artificial intelligence to help various sorts of industries to economize on the way they deal with language or with forms or letters or correspondence and so forth. And so he has a system which can convert certain kinds of documents into formal logical formulae. But in addition to his company, he's also working on more general research issues, one of which has to do with the mathematical representation of language generally, and the other of which, and that's where he and I have been collaborating now for some years, is in various fields of philosophy, including the philosophy of AI, but also in other areas of philosophy. And we are at the moment finishing a book called There Will Be No Singularity. The singularity is a doctrine defended by some artificial intelligence aficionados, according to which AI machines are going to get more and more intelligent to the degree that they will be able to replicate themselves in even more intelligent machines, thereby setting off a snowball explosion and taking over the universe. So first they'll take over this planet, which will take them not very long, but then they will go out into the galaxies and take over the entire universe. This is called the singularity, and the idea that there will be a singularity is, as we will show, as we try to show in the book indeed, nonsense. These are the chapters. We start with a discussion of the difference between human and machine intelligence. Then we talk about language, what exactly it is that humans are able to do because they have the intelligence to use language. And similarly, we talk about social and ethical behavior. And then we come to the central chapter of the book, which is about complex systems, the mathematics of complex systems. The brain is a complex system. The human body is a complex system. Human societies are complex systems. And complex systems, roughly speaking, are defined by the fact that they involve many, many variables, which means that the usual equations of the differential calculus and so forth cannot really be formulated and solved in any sensible and useful way when we're dealing with complex systems. And the rest of the book is dealing with the consequences of the fact that the mathematical treatment of complex systems is very, very weak. And since machine intelligence would require a mathematical treatment of something like the human brain, it follows that there can be no machine intelligence. And then we draw conclusions from this about the Turing Test, about the possibility of having an ethical AI, which some people worry about. And we conclude, first of all, with a chapter on more nonsense, which is the idea that human beings could become immortal by uploading the contents of their brains to the cloud. And then the final chapter is about how AI will nonetheless have a useful and prosperous future, just not general AI, the sort of AI which has intelligence of the sort which human beings have. or indeed vertebrates. So they will, the intelligence that is possible with a machine will always be considerably less than the intelligence which is achieved by crows or parrots. All right, so I'm only going to talk about chapter 2. And there are 3 parts, as you can see. One is about what some people call powers. I'm not going to make any jokes about the powers metaphysic, but I am going to talk about special kinds of powers, which are dispositions, particularly of human beings, and capabilities, which are special kinds of dispositions. And then I'll talk about intelligence, which is a special kind of capability. And that's the heart of the talk, although it's only a small section at the very end. I'll talk about machine intelligence and how it's defined by its advocates and problems with their definition. So these are all the dispositions. There are many of them, and they are physically grounded, realizable entities. So examples are to grow, to go bald, to die, and so on. We all have those dispositions. All the males in the audience have these dispositions. And all habits, all skills, all instincts, all diseases, many, many things are dispositions. And capabilities are special kinds of dispositions. They are those dispositions which an organism or a group of organisms, or potentially also an artifact, we'll come back to artifacts later, has an interest. So we all, as organisms, have an interest in surviving and reproducing. And higher organisms, like human beings and mammals, have also an interest in the survival of our offspring. And so we have lots of capabilities which contribute to survival and reproduction. For instance, the capability to digest food, to kill our enemies, and so forth. But then in addition to those biological dispositions, we have other kinds of interests which gives rise to non-biological capabilities. For instance, the capability to speak Italian, the capability to perform a scientific experiment, to pray, to vote, to own a factory and run it, or to employ people, or to be employed, and so forth. These are all non-biological capabilities. They are capabilities which reveal that human beings have a surplus drive or an excess drive to do things beyond the realm of the merely biological. And intelligence in human beings accordingly comes in 2 forms. One is the kind of intelligence which other organisms, like many vertebrates, have, which is the intelligence needed for survival and reproduction in one's adapted environment. And then there is the higher kind of intelligence, which basically involves the use of language, planning, and so forth. All of this will become clear as we go along. All right, so we have dispositions, and then we have capabilities, which are those dispositions in whose realization we have an interest. And we could be just the individual who has the disposition, or it could be the family or the country of the person who has the disposition, or it could be the owner of an artifact which has the disposition. And in each case, because there is an interest in the realization of the disposition, there is a capability. Now, we could spend the next 90 minutes or so arguing about the good sense of this definition of capability, but we're not going to do that. All right, so these are some examples of dispositions and also some examples of capabilities. And we will revert to these examples later on. These are just to give you a preliminary orientation. Now, I'm not going to talk very much today about functions, but functions are special kinds of capabilities. John's digestive system has the function to digest food, and therefore John has a capability to digest food, but it's not John's function to digest food. Why not? Because in order to be a function of X, a capability has to be the reason why X exists. So in the case of an artifact, X has been designed to perform this function. That's why we created X, because we needed something to hammer nails. And John was not designed in that way for anything, except potentially for surviving and reproducing, but certainly not for eating. And so it's not a function of John to eat, but it is the function of John's digestive system to digest the food that John eats. And so this is the simple story, and the function part will play a role, but a very small role in what follows. All right, so organisms can have capabilities, your digestive system can have a capability, and groups of organisms can have a capability. For instance, a football team, and artifacts can have capabilities. It's unclear whether this artifact has any function, but it certainly has many capabilities. And that's because there are owners and sellers and makers of this artifact who have an interest in its realizing a number of different dispositions. All right, now we've had the definition. Capabilities are dispositions which some organism or group of organisms has an interest. So there are no capabilities on Mars until organisms start thinking about or actually moving to Mars. There are only capabilities where there are organisms. There are dispositions all over the place, but only some dispositions are capabilities, and every disposition which is a capability is so because some organism or group of organisms has an interest. And as we saw, there are two kinds of interest and therefore two kinds of capability. All right, now the human brain has a part which is a fiat part. It has vague boundaries, and it's a slightly different part from one human being to the next. But it has a part which develops and has a reason to exist because the human being needs to have some part which has as its function to think and reason and use language and plan and concentrate and do all of the other things that go hand in hand with intelligence. And because we have this brain part which develops in the first years of life, which has this function, it follows that we have the capability called intelligence. So our capability of intelligence has its physical or material ground in a certain part of the brain. Potentially also, this part may extend beyond the brain, but we will come back to that question later on. Okay, so this is human brain development. The sensory parts begin first, and then the language parts begin. And in each stage, there are changes which occur in the brain in order to bring about this part of the brain which has this particular function. All right, now, there are, in the history of the study of intelligence, a number of classical definitions. And we picked out two of them here because they play quite a dominant role in the history of psychology of intelligence, and because they are relevant to the artificial intelligence definition of intelligence. So the first one says that intelligence is just the ability to adapt to new situations. And this works to a limited degree, as we will see, but it does work for vertebrates who are foraging for food, for instance. Vertebrates can find new food. They can move from one environment to the next and adapt to the new environment in virtue of their intelligence. Amoeba can't do that. Although we'll come back to that question later on. Maybe they can. And then the second one is the mainstream definition of what is sometimes called the general mental capability, which involves not just the ability to adapt to new situations, but also the ability to create entire new environments, to reason, to plan, to solve problems, to collaborate with people, and so forth. So this is the kind of intelligence which is unique to humans, where the Stern definition is found in practically all organisms, certainly in higher organisms. Now, when we were working on these ideas, we were drawing quite a bit on the phenomenological movement for a number of reasons, not merely having to do with the biography of myself and Jobst, but also because we thought that they had good ideas which had not been sufficiently explored. And one of these phenomenologists is Max Scheler, who had quite a lot to say about the mind-body problem in connection with his discussion of intelligence. And so he identified a kind of intelligence which we call primal intelligence. And this primal intelligence is typical of most vertebrates. And it's the kind of intelligence which is realized in addressing biological needs. So this is the idea mentioned earlier about survival and reproduction. So all organisms have an interest in survival and reproduction, which means that the capabilities of those organisms to survive and to reproduce are addressing biological needs such as drinking and eating and so forth. And primal intelligence is the power, according to Scheler, of making a meaningful response in the face of a new situation. And this meaningful response is important. Meaningful response means it's a response to the situation which is in the service of the drive of the organism to survive and reproduce. So it's meaningful to the organism that it goes after a specific kind of prey, or that it avoids a specific kind of predator, and so forth. And this is a kind of intelligence which is shared by humans also. It's not something we learn. We have it innately. In order to be a marker for intelligence, the response has to be novel in Scheler's terms. It has to be immediate. And it's tied to the adaptive environment of the organism. So it's organically bound in Scheler's terms. It's a process that the organism executes in responding to a new situation in the service of an instinctive behavioral urge. So these are the four features of primal intelligence as we identified them. And as I say, these are features which you find only in non-human animals. And non-human animals live to fulfill immediate goals in their adapted environment. They always live in the present situation. They can't abstract away from the present situation. And their perception is filtered to a very powerful degree. So they ignore stimuli that are not tied to their need to survive and reproduce in much the same way that we ignore ultraviolet light or radioactivity when we are perceiving the world around us. We, of course, being human, could go beyond this primal intelligence and build artifacts which can measure radioactivity or which can be sensitive to ultraviolet light, but non-human organisms can't do that kind of thing. All right, so why do animals have intelligence, and how do we know that they have intelligence? Well, first of all, we know that they have consciousness because they have perceptions. We know that they have perceptions because they have to go looking for food. So organisms like parrots and dolphins have to forage for food every single day. And they display their primal intelligence in the ways that they forage for food. They go searching, which is more than just responding passively to sensations. It's a matter of physical activity. And the physical activity of searching involves feedback loops between the ways they perceive their surrounding environment and the ways they move, for instance, to avoid predators or to reach out to grasp food. They can identify new food sources, which is a kind of categorizing activity, which is quite sophisticated. And they can communicate with fellow group members in order to warn them of predators or to inform them that food has been found. And then they can fight their competitors. And they can do this very quickly. They can adapt to new food sources very quickly. And this, again, is a mark of primal intelligence. So they're quite intelligent, more intelligent than the most intelligent computer when it comes to general intelligence. And I'll come back to the question of general intelligence later on. All right, now, again, under the influence of Husserl, who talked about objectifying acts, by which he meant acts which are about objects, mental acts which are about objects. We defined another idea in Scheler, which we call objectifying intelligence. And it's objectifying intelligence which sets humans apart from non-human organisms. So we can conceive and plan and build new kinds of artifacts, new kinds of environments, indeed. Artifacts that will enable us to survive where human beings could not survive. Igloos are an example. Spaceships are another example. And we can do this because we can rest on the shoulders of our ancestors in a way that non-human organisms cannot do. And this means that we manifest what Boyd and Richardson, who are two anthropologists whose views we find very congenial to our approach, what they call cumulative cultural evolution. And what this means is that while organisms of many sorts can learn by observing what other organisms do, they just learn one trick. And then when they die, that trick is forgotten. They can't build on the tricks of the previous generation to create new and more complicated tricks, such as language, for instance, which is a very complicated collection of many, many tricks, which was learned over many generations by our ancestors, and which we are still learning and still creating new levels of complexity for. All right, so this cumulative cultural evolution is in some ways analogous to the evolution of the genome, which occurs at the level of biology. But where biological evolution applies to all species, we are the only species that has succeeded in activating cumulative cultural evolution. And that's primarily because of language. So it was language which gave us the ability, above all, to pursue long-term goals. Language plus security. So an organism will not pursue long-term goals if he knows that he's going to be dead within a few hours or a few days, or if his species is such that all of the species members pay no attention to the long term because they would be dead anyway. Humans have enough security that they can pay attention not merely to the long term of themselves, but also to the long term of their ancestors. So we can formulate wills and testaments which give instructions to those who will survive us as to what to do after we die. And we can build the Large Hadron Collider and other gigantic edifices which take multiple generations to develop and perfect. All right, now, what this means is that, and I talked earlier about surplus drive or excess drive, humans have a kind of drive to build these more elaborate environments. And that means that they are adapting to the planet in a much more radical way than animals do. We create man-made environments, including Google and Facebook and the technosphere generally. So we are changing the world. We can shape our natural environment to make it fit our needs and desires, and our needs and desires too are subject to cultural evolution that is cumulative. And this kind of cumulation, as I say, is impossible for non-human animals. All right, so objectifying acts are that which manifests objectifying intelligence, and it consists in doing things like asking questions. So in other words, exhibiting curiosity as a collaborative action, doing science, in other words, reasoning about the next meal or where you're going to go for your holidays, thinking about how you're going to have enough food for later in the evening when all the shops are closed, or doing mathematics or architecture or music or any of those other things, all of which require at least some form of language or symbolic vocabulary. And that's the characteristic of objectifying intelligence guided activity, that something like language is involved. And these are then the capabilities which objectifying intelligence consists in. And we all know what they are. These are the cognitive capabilities characteristic of human beings that you do not find in cats and dogs and things. So we can reflect upon ourselves as objects standing in relation to other selves, and plan on behalf of other selves, and guide other selves, and gain authority over other selves, or subject ourselves to the authority of other selves in all kinds of complicated ways, sometimes involving uniforms and badges and so forth. And I mention that only because nothing like uniforms and badges is found in non-human animals. That is not a trivial statement. All right, now we're getting to the important part. So non-human animals have minds and brains. But we're interested in the minds and brains of humans. And there are some features of the relations between the minds and brains of humans which are common to all of us, we assume. So there's very much in common in our perceptual systems from one person to the next. There's very much in common in the ways we use language from one person to the next, as is evidenced by the fact that we follow very much the same rules when speaking. Some people speak with funny accents, but most of us, we get away with speaking a non-funny form of our language. And but there are other features of the relations between our minds and our brains which vary from one individual to the next because of small or large differences in our genes, or in the way we were brought up by our parents, or other random factors of the environment, potentially also the prenatal environment. So there are many features of the mind and brain which are shared, but there may be equally many, maybe more, maybe less, but still many features of our mind-brain relation which are specific just to each individual. Now, if we are going to understand the mind-brain relationship, and that's what we have to do if we want to realize artificial intelligence, at least following a certain strategy, which I will describe in a minute. If we're going to understand that relationship in a way that would allow us to predict how the mind will function given certain brain scenarios, or how the brain will function given certain activities of the mind, which we can identify, for instance, because someone is speaking, then we would have to have a very, very detailed understanding of the functions of all the relevant cells in the brain, and of all the functions of all the cell constituents in the brain, all the way down potentially to individual molecules. So all of the things which contribute to our consciousness and to the mental phenomena of reasoning and so forth based thereon are going to have to play a role in understanding how mental phenomena arise, not just at the level of general psychophysical relationships, but also at the level of instances of individual human beings. Because one human differs from another in certain ways in how their brain is coded for mental activities. And this is not just in the brain, it's also going to apply to other parts of the body. For instance, the endocrine system, the pain system. All of these bodily systems too have components which contribute to the way the brain works mentally. And all of them involve, again, many components at the cellular level and at the subcellular level, all the way down to individual molecules. And to understand these connections, we would have to do this at the level of individual instances, at least in regard to certain features of the relevant relations. So we'd have to understand the molecular configurations of all neurons with sufficient detail to allow us to understand their dynamic interactions with mental processes. And that's what we would need in order to realize artificial intelligence along one strategy that I will identify in a minute. Now, there is something in physics called the three-body problem. You have 3 point masses, and you know their initial positions and velocities, and then you try to predict their subsequent motion using Newton's laws. You fail. The three-body problem is not solvable. And now, in order to understand the relations between the molecular configurations of neurons and the mental processes associated therewith, we are facing something like a trillion-body problem. That problem, too, is not solvable up the wazoo, as we might say. So the strategy I have in mind is called whole brain emulation. It's one of 3 strategies which are mooted as means whereby we could create artificial intelligence in a machine. And whole brain emulation, I think, is the most attractive strategy, or it's viewed by its advocates as the most attractive strategy. And it's the strategy that we deal with at greatest length in the book, but there are other strategies which I will talk about briefly. So the second strategy, which some people find attractive, is called evolution emulation. The idea is that instead of trying to emulate the whole brain of, for instance, a somewhat intelligent human organism, we would try to emulate the evolution, the steps of evolution which led to that whole brain or to something with an equivalent intelligence. So in other words, we would create what is called artificial life inside the computer, and then we would subject this artificial life to the same kinds of processes which occurred in real life over the course of evolution, and eventually, and quite quickly, since machines can do these things quite quickly, we would reach the evolution of artificial life at the level of intelligence of the whole brain. Now, the first problem with evolution emulation as a strategy is that it's much more difficult to implement than whole brain emulation. Why should we go to the bother of emulating all of the billion years of evolution in order to reach the end point, which is the emulation of the whole brain, when we could just focus on the whole brain and emulate that, which is an almost infinitely simpler, even if still incredibly complicated, problem. So that's the problem with number 2. I have the impression, and Jobst can confirm this later if he wishes, that the artificial life movement is more or less dead, that it's become a little bit like relevance logic. It's become an area of research which aficionados pursue, but no one else is interested anymore. But I'm not sure about that. Then thirdly, we have algorithmic approaches to artificial intelligence. Now, the one I like best is good old-fashioned logic-based AI. But it doesn't work. You're not going to get anywhere near the appropriate degree of detail using good old-fashioned AI, because we don't have the time to write all the axioms, and we don't have a way of making the axioms write themselves automatically. And so while it's still a very interesting approach and still valuable in many ways, and Jobst actually uses it in his company, it's not going to be able to solve the problem of creating an artificial machine, artificially intelligent machine. And then finally, we have stochastic approaches to artificial intelligence, and they are certainly the most fashionable. But I think that the most fashionable of these most fashionable approaches, in connection with the issue of creating an artificial intelligence, is actually using stochastic AI, which means deep neural networks, in order to create a whole brain emulation. So in other words, the third route in its most influential form currently is in fact identical with the first route, the whole brain emulation. And so we're back with whole brain emulation, ladies and gentlemen. All right, so how do the AI community, which means the community of stochastic AI, now I guess I should explain what stochastic AI means. So if you do good old-fashioned AI, you have human beings who sit down and write axioms. And then you have a lot of axioms, and you can use those axioms to reason about simple physical machines, for instance. In stochastic AI, you have a huge amount of data. And a good example would be a spam checker. A spam checker is a piece of stochastic AI where a machine is trained to recognize spam because you feed the machine billions and billions of tuples, where the first member of the tuple is an email, and the second member of the tuple is a yes or a no, created by some recipient of the email who identified that email as spam. If you have billions of those tuples, because spam features are spread quite evenly across the whole space of emails, you can use stochastic AI to generalize to new emails and identify them automatically as spam. And feeding in those billions of tuples is called training the neural network. And so for stochastic AI to work, you need very large representative training sets of tuples, which can tell the machine the patterns it needs to look for, and then the machine can use those patterns to identify facial features or email spam or other things which AI machines are incredibly good at, or so people say, and they're often right. All right, so the mainstream of AI research now is stochastic AI. What we say in our book, and what I'm going to be repeating here, is that the arguments that we put forward against the possibility of replicating intelligence inside a machine apply not just to stochastic AI, but to any conceivable form of AI. And this has to do with mathematical features having to do with the idea of Church-Turing computability, which I won't go into. All right, so how do proponents of stochastic AI define intelligence? The answer is to go back to the old Wilhelm Stern definition, according to which intelligence is an agent's ability to achieve goals in a wide range of environments. And here an agent might be an organism, or it might be a Turing machine, or an AI algorithm running on a Turing machine. All right, so the problem here is that now a very, 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 very small worm, such as C. elegans, turns out to be intelligent on the basis of this definition. So C. elegans can forage and reproduce on many kinds of environments and use snails and slugs as migration vectors to move from one environment to the next. So C. elegans, which has just 302 neurons, this would be a 302 body problem, or at least 302, actually a lot more, because you need to take account of all the molecules. But still, it's stupid. C. elegans is stupid, but it turns out to be intelligent according to this definition, which is the definition, as I say, which is accepted in a paper with the title Universal Intelligence as the definition of intelligence, not just for machines, but for anything. All right, so this is the beginning of the definition. I'm not going to talk for very much longer. So we have to think about achieving a goal. So it's not enough just to exist in an environment. You have to achieve a goal. And so how do the proponents of the Legg-Hutter definition of intelligence define the specific feature of achieving a goal. Well, they do this in terms of utility. First of all, we have an action which involves, it might be playing chess, for instance, which involves a series of steps. And with each one of those steps is associated a reward. And so R subscript I would be the value of the reward at step I. And for mathematical reasons and without loss of generality, we assume that there is an infinite number of steps. Then the V pi mu defines the expected utility across this sequence of steps. And it's defined in such a way that it's always less than one. Again, just for mathematical simplicity reasons, which bring no loss of generality. So there is this mathematical definition of utility. And just to go a little bit further, so the sum of the rewards Ri achieved over a series of steps I is the utility for an agent pi in the environment mu. Now, one big problem with this definition is what mu is defined as. And if you examine the text, this classical text called Universal Intelligence, you will see that mu is defined as the minimal binary description of an environment. Now, by minimal binary description, what they mean is a set of tuples, actually of two tuples. The first, well, I don't need to go into that in any further detail. The idea is that when you're dealing with an environment, somehow you're going to be able to specify the environment by collecting what may be a very, very large number of binary tuples. Now, that may work in a very abstract kind of setup. It may work, for instance, when the task which is being addressed over the series of steps is something like proving a mathematical theorem. Then it might be right that an abstract structure like a series of binary descriptions would be adequate to serve as the environment. But and then if we're talking about a very, very constrained environment, for instance, a robot which has been programmed to clean up a nuclear power debris site, it may be that all the robot needs to know is binary tuples specifying locations in the site which have either already been cleaned up or which still have to be cleaned up. So for each point on the coordinate system, you associate a y or an n according to which it's been cleaned up or not. So for the intelligence of the robot cleaning up a nuclear power debris scene, this definition would work. This definition of environment, I mean. For a computer doing mathematics, this type of definition of environment might work. But for a crow hunting for whatever it is that crow hunt for, it doesn't even get off the ground. Because there's no way in which we can understand the environment of a crow or a parrot or a dolphin or a human being as a binary description. And so this is not a universal definition of intelligence. This is a definition of something which is convenient for people who think that intelligence can be realized inside a computer, and who thereby need a way of having a perfect replica of an environment inside a computer. And this they achieve by simplifying environments so that they become binary vectors. All right, so this repeats what I just said. So this may work in artificial environments, but in natural environments, signals emanate from complex systems. And this is another trillion body problem. We cannot solve this problem. We cannot create a system which can perform mathematics over natural environments in such a way as to emulate the way organisms, even parrots, deal with natural environments, because there are too many variables. All right, and now finally, there is another problem, which is with the steps. So not merely is the environment a problem, but also the idea that when we are reasoning intelligently or performing intelligent activities, that we are reasoning in a series of steps, with each one of which there would be associated a certain reward so that we can sum over the rewards. Now, this is true if we're playing chess, but for practically any other kind of activity, it's not true. There are feedback loops between perception and activity. When I perceive something, for instance, a predator with a machine gun who's following me, then I act in such a way as to adjust my perception and avoid being killed. So perception depends not just on sensory stimulus. Along those lines, one may do quite a lot of work with a binary vector. It also involves the observer purposefully acting in response to what the observer perceives. And this depends on another massive payload of brain and mind internal variables. And mu does not capture any of what is involved in this dynamic feedback loop system between action and perception. Purposeful human activity rests on a fine-tuned interaction between perception and motion. And how that works, we hardly know. Even the most ambitious and successful neuropsychologist does not know how this kind of synergism between different body systems works. Certainly not at the molecular and neuronal cellular level. We don't know how it works. And we certainly don't understand how it works. And therefore, we can't program a computer to replicate how it works, because this is yet another trillion body problem. And that's the end.
Thanks, Barry.
Good. So the first question is a very good question, and it's a question that Jobs and I have never discussed. He may have good ideas in response, but I think one of the implications of the view that we take is that multiple realizability is impossible. So it cannot be the case that the kind of processing which goes on in a human brain could be realized in any other sort of artifact or organic entity. I think I'll just let Jobs tell me whether he agrees with that.
So I with pleasure, and I'll also answer, if I may, the second question. So to come to the first question, so of course there may be other intelligent species with kind of objectifying intelligence somewhere in the universe, but they would be kind of with high likelihood different, because the way that this intelligence would be realized would be different structurally. And so I think that probably I agree with Barry that the intelligence we have and that we can describe in the way, for example, Max Scheler did, is probably unique human capability. But of course, there could be other intelligences that have spontaneously evolved somewhere else in the universe. Regarding the second question, so it's true that the three-body problem can, of course, be numerically approximated. But when you get to higher, and it can be approximated actually to an extent where the solution is so good that it's overshadowed by the measurement error, which means that the measurement error becomes more important in distorting the result than the procedure for computation itself. However, this is not shown for the n-body problem. So the n-body problem is really a good example of an uncomputable problem, because if you think of the human brain with 4 billion neurons, each of which has hundreds of millions of actually millions of molecules in it that determine its function and determines also its behavior with regard to other neurons, then n becomes in the quadrillions or trillions, and we have no way in mathematics, and we show this in the book where we go through all the methods that are available in mathematics for solving such problems, that we cannot neither find an implicit nor an explicit solution with no available method. And so that's what I believe. And it's actually even true for much more trivial problems like turbulence. Turbulence is an inanimate problem. Yeah. So I was skiing last week, and the wind was blowing against the snow, and you see these turbulence of very tiny snow particles blown in circles by the wind. It's a very beautiful sight. But each of these events is actually unique, unrepeatable, and cannot be modeled. So you can't. We've tried now since 150 years. We cannot get a model for how these particles move, although we kind of know the forces that work on them. We can't do it. So there's a huge part of inanimate nature even that we cannot get close to modeling. And Heisenberg actually said, when I die, I want to ask God two questions. The first one, why is there relativity? And the second one, how does turbulence work? And then he says, and I believe God will have an answer to the first question.
Thank you.
All right, Lewis, you're on next.
So my question is a follow-up to the question that Aaron asked during the break. So the question that Aaron was asking during the break was about whether an intelligence would have to model the environment, if I'm remembering it correctly, whether an intelligence would have to model the environment fully in order to qualify, or whether it would be okay to have like an only partially modeled or an artificial abstracted environment. Part of why I was curious about that is, I guess, not to give you too much of an opportunity to dunk on me, Barry, but like, I'm worried that I don't qualify as a human level intelligence on your account. Because I feel like, I mean, I understand the structure of the argument is that like a computer can't simulate my brain because there's too many neurons, but like I don't keep track of like, I'm not keeping track of infinitely many things in the environment. Like, I'm not sensitive to the number of different things. So like, sometimes I'm sympathetic to like Humean infinitism about things. Like, I'm worried that like Descartes was wrong about whether we can genuinely conceive of the infinite, and that like I'm really just a discrete computational device in a way. Yeah. And so I'm worried that if that impulse on my part is true, that I'm more like, maybe not all the way down to Conway's Game of Life, but like that I might be not my brain per se, but like the part of me that's doing the thinking, at least, some abstraction of my brain might be more simulable than you are allowing for, even if my brain is not.
Good. So I think we can address this by means of a story about driverless cars. So 10 years ago, people were incredibly enthusiastic about driverless cars, and they thought that we would have driverless cars within 5 years. But then about 5 years ago, when there were no real developments apart from a few accidents, this enthusiasm waned quite considerably, and now people are much more careful about the kinds of predictions they're making about driverless cars. So how does the driverless car story go? We start by creating small, highly controlled environments in which funny shaped cars with lots of gadgets, LiDAR and radar attached to them, drive around in very controlled ways, and they are steered by computers. So we have driverless cars, but only in a very controlled environment. And now that's not good enough. You want to have driverless cars which are in the real world. So you make the environment a little bit less controlled. Instead of just having Disneyland, you have Disneyland plus the road from Disneyland to the airport. And then there's an accident. And so you realize that the software you were using in the controlled environment can't extend to the slightly less controlled environment. And so you revise the software, you get a more powerful software. And so a more intelligent software. So now you think, well, we're getting closer to all we need to have driverless cars whose software is as intelligent as human drivers, Lewis, for instance. And so you tweak the environment a little bit, you make the environment accommodate weather, you allow people to drive in the rain, you allow people to drive in snowstorms, you allow people to drive not just on the roads in Disneyland and to the airport, but also on the roads around the airport and a few other roads. And then you have another accident. There's a political demonstration or something, which the software didn't expect. It didn't know about political demonstrations. Or there's a moose which escaped from the zoo and ran into the middle of the road. The car didn't know what to do, and so people died. And so you go on. Each time you make the driverless car slightly more intelligent in order to cope with a new environment. Now, that's the approximative kind of approach that you are envisaging. So according to this, you only have enough intelligence to drive along certain roads, but there are traffic conditions that will kill you because you just don't have that little bit of extra intelligence. Now, I don't think that is the way that human intelligence works. I don't think it's like software, which is keyed to a given environment of a given complexity. I think that the human intelligence is much more like an ocean wave or the water in a complicated system of pipes. The water will just flow to reach its goal. It doesn't have a level of intelligence. It doesn't have a level of software. It just has a very elegant, tested series of spontaneous reactions which have been built into it over 3 billion years of evolution. I think that's what you have. You have that kind of multifaceted, spontaneous reaction system. One day, an environment will kill you, but that's not because you've suddenly been led into a slightly more complicated environment than the ones you were living in until yesterday. It's because something went wrong.
I mean, I would like to add one thing that's very important, Louis. So Gehlen, who a follower of Scheler, says that a very important characteristic of human intelligence is actually the ability to exclude aspects of the environment. And so what you're describing as your finiteness or your inability to cope with everything that surrounds you, actually you're the proof of your intelligence. Because an animal that has primal intelligence can only cope with certain predefined pattern of the environment, but you can freely choose what you're focusing on. And so this is actually a sign of your intelligence.
So I would agree if it were the product of me choosing to screen things off, but I'm thinking about things more like if you read like Cialdini's Influence, Science, and Practice, and you're thinking about it from like a social psychology perspective, where he likens a lot of human social psychology to the like very like contiguous with animal behavior, click-whir style automated responses that have the appearance of like sophisticated intellectual behavior, but are in fact more reflexive automated procedures. So for example, one of the examples that's used in the book, I don't know if this is going to be the best example, it's just the first one that comes to my head, is like people have a tendency to do like perceptual, like they do very perceptual comparison. So you can take advantage of that if you're a store owner. You just like mark everything as though it's half off, but keep the prices the same. And then all of a sudden you can improve your sales a lot by just having everything marked as though it's half off. And like people just all of a sudden think that they're getting good deals when they're not. That's not like going to be the best example I could have come up with if I'd thought of it for a while longer or like had the book right in front of me. But like that's not actually Vida just put in the chat, appearances of scarcity, widespread appeal. So like that there is, I think, a case from like social psych research for there being an appearance of a lot more sophistication to these things that is a byproduct of the interaction of a lot of maybe more animalistic primal things sort of coming together. And so
I think, so Well, part of our argument is precisely that we evolved from lower organisms over a very, very long, complicated period. So a lot of what we succeed in doing intelligently and successfully, we do because we employ tricks, which we learned through biological evolution, not because we're intelligent, but because in fact, I even formulated it in this way in the talk. We have a huge store of evolved tricks, some of them very high level, some of them low level. So that you may have heard of the cheetah detector mechanism. So we have evolved to be able to detect cheetahs of a certain sort.
Sorry, you're not talking about the feline animal, but rather somebody who fails to follow the rules, I take it.
I'm talking about somebody who tries to cheat you in one way or another with a deal, or somebody of the opposite sex who is trying to get you to do something which you really shouldn't want to do. So we have a cheetah detector mechanism. It's a very, very primitive part of Lewis's intelligence, along with all the sophisticated parts. So we have nothing against the fact that there's a lot of biological intelligence built into the human being.
Actually, the point we even make is that this part of our intelligence, even this part, the primal intelligence that we share with other mammals and vertebrates, cannot be even this cannot be emulated with artificial intelligence. So this type of intelligence is already much too complicated and sophisticated to be programmed into machines. And so even if your argument was right, that there is no real big difference between humans and animals, which obviously is, I think, wrong, because there is human culture, which animals are not capable of, at least not in this form. And even if that would be right, it still would not contradict our argument that machines can't actually emulate primal intelligence.
Okay, let's see. Next in line is Neil Williams.
All right. I feel like I've been cheated. My senses are tingling. No. I can see why developmentally, if we're trying to bring something up, that we enter immediately into sort of like 3-body and plus problems. But what I didn't see was the step where we moved the other way. There was a slide where it said very quickly, well, if we're trying to model mind and brain, we need to do this, immediately at a kind of cellular level, which is sort of strange because most of the other modeling we do for any other organ or function isn't cellular. I can't explain digestion at a cellular level. Barely. I certainly can't do it at a physics level. And so, it seems like the relevant explanations are not going to take place at that kind of level. Now, it may be that the step is something like, well, if you're going to do it with a computer, you have to be able to do it at that level to be able to build it back up. But I don't know that I heard that step. So I will sort of ask you to therefore intervene.
Do you want to do this, Jobst, or shall I?
Yes. I would like to take first step at it. So basically what you're describing is the fundamental lack of explanatory models in biology. So as you all know, there are 3 levels of science. There's description, explanation, and prediction. And so and explanation and prediction can get very close to each other if the explanation is given by an equation. Yeah, then if the explanation is correct, you also have the prediction. And biology is mostly descriptive science still. So it's true that we don't know, for example, in detail how the liver works, to take a digestive organ, or the most. But let's take a more simple one. Let's take really the intestine. We have some models of the intestine, but they're mostly descriptive. They have also explanatory aspects, but surely we cannot rebuild an intestine from scratch, because our understanding of the intestine is much too primitive. And that's, to speak with Rudolf Virchow, who was the first physician and biologist to recognize how the body works, is that it's working by cellular function. So if you wanted to fully understand the intestine, you would have to understand fully how each cell of the intestine works, how it collaborates with the other cells to yield the function of the intestine. But even for the intestine, nor for the skin, nor any other part of the body that is simpler, nor even for the bone, which is even simpler than the skin in some ways, have we understood the causalities and can give a causal description. We can only give causal explanation. We can only give descriptions. So that's why we say we would need a cellular level explanation of the brain to understand how it works, to rebuild it in a machine.
That seems a hint unfair to the sort of levels of descriptions we've got with, like, I mean, organ replacements, for which, granted, I don't think we can build the liver from scratch, but let's say we can replicate all the functions of the liver such that I can have an artificial one. That seems pretty good. Well, we can't with the liver. We can't with other stuff. You can do a heart pretty well. We seem to do
no, we can't. Actually, we can't. We can transplant a heart from an animal to a human or from human to human, but you cannot build an artificial heart that works midterm. Maybe a few days, or a few weeks, but we have no artificial heart that is functional right now, because actually, so I disagree. I think that we are that the properties of living systems make it so hard to model them that we actually can do very little if we don't use biological material that's already living.
Perhaps. I mean, don't we have artificial kidneys? They're very large and they're very complicated. But I mean, we don't know, I suppose, internally how kidneys work, but we know what kidneys function for. I mean, and I'm not saying that helps the AI situation any, but it means that we might be able to operate at a slightly more black box outsider level than, rather than getting in the inside and building one from particles, as it were.
So, Neil, have you seen this TV program called Uploaded?
No.
So it's a future world in which people can choose to die and then be reanimated in the cloud. And when they are reanimated, they wake up in a really attractive, elegant hotel overlooking a lake, and all the women around are very beautiful and so forth. And the food is fantastic. And they are then immortal. And they can even talk to their girlfriend on Earth, as it were. And now, in order to make the choice that you're going to pay the $4 million or whatever it is in order to enjoy this immortality, and you'll never be able to check whether they were cheating, you would have to have a very strong reason to rely on the fact that the brain software, which is in the device, the cloud device, which is going to contain the simulation of you, is down at a very, very low level, the same as your brain software. You don't want someone else to be enjoying all that nice digital food. You want it to be you, because you're paying the $4 million. Now, are you going to be satisfied with some approximation like the artificial kidney, which is
perhaps
probably not?
Yeah.
No, you will want good cell level or neuron molecule level based prediction. You can't get it, and that's why you will never be immortal.
All right, Neil, you're done for the moment? Okay, I have just one person waiting for, before I go to Harjeet for another question, I'm going to call on Aaron since he just raised his hand. Go ahead, Aaron. Aaron? Looked like your hand was up.
Seems to have disappeared.
That's interesting.
He disappeared. Maybe he was saying goodbye.
Maybe
no.
he was
there. You know, that was weird. I don't know what happened there. That was
okay, speak up or turn up your volume or something.
Yeah, can you hear me now?
Yes, yep. But it's a little hard.
Okay, sorry. So basically, the whole upload that's interesting. You didn't mention the Turing test at all, because again, it's like you definitely do want to make sure it's really you. But if everyone believes it's you, if the quality is that high, then aren't you fine? Haven't we reached intelligence if people believe it? No.
Well, you're fine from the point of view of intelligence. You're not fine from the point of view of Neil finding it worth his while to spend $4 million. He wants it to be him. He doesn't want people just to believe that it's him. But
furthermore,
I'll just say the longest chapter in the book is a demonstration that there will never be a machine that can pass the Turing test.
Really?
Yeah, and the reason why you cannot pass the Turing test is that there is no, to try to put it in a very condensed form. So if you want to create an algorithm that can pass the Turing test, you would have to have a distribution of data that is an adequate training sample for an algorithm to learn a language. However, it can be shown that such distribution cannot exist. And the reason is that there is the process of language generation is non-ergodic. And so that's explained in the book, but it basically means that the process never gets the same distribution twice. And so when you pick samples from distributions and try to use these to train the algorithm to learn language, it will always learn on something that is not repeatable. And therefore, there is no adequate sample to train. And that's also true for other methods than training. So there's just no sample that can be used. And that's why the Turing test can never be passed. And I think that's probably the hardest, the part of the book that is the toughest in rejecting the notion of general artificial intelligence, because obviously without language, there can't be intelligence. And we prove that actually you cannot emulate language with a computer.
How did you prove that you can't emulate language with a computer? It's like the white raven, right? How can you prove something that doesn't exist?
Oh, well, what we do is we make, of course, we have some axioms. And one axiom that we use is that we believe that the mathematics we have today are not going to change so radically that we will be able to model emanations from highly complex systems. And if this axiom doesn't hold, then it could be done someday, but we are much farther away from this than the Neanderthals are from Einstein. The step from a Neanderthalian way of counting, I think they could count 1, 2, and then many, is much closer to Einstein's general theory of relativity than we are now with our mathematics for modeling complex systems. So at the moment, I think with the genetic endowment we have and the innate capabilities we have, I don't think we can model such complex systems. And what we do in the book to give plausibility to this hypothesis is that we walk through the complete realm of mathematical modeling to see whether there is a method available that could be used to model such systems. And we, of course, also use the latest publications of the complex system modeling crew or interest group to show that they can only model very small aspects of complex systems, mostly descriptively. And that has to do with the nature of these systems. So, but of course, the proof has an axiom, or that if you don't buy this axiom, you can say, well, it's not a proof.
That's fair. Thank you.
Okay, let's go to Harjeet. And if anybody else has a question, please.
Okay,
Fire away.
think I am off mute. Can you guys hear me?
Yep.
Yes.
Okay, so I just wanted to come back to, I think, a point that was raised earlier about sort of a minimal rationality. This sort of idea that's been inspired by Herbert Simon outside of philosophy, and within philosophy, people like Chris Cherniak in his incredibly good book, called Minimal Rationality. And so the idea is basically, look, I think Professor Smith described language as something that, you can't learn, but in some ways is genetically passed down and is part of the genetic endowment of the organism. And then all these failures that individuals make mentally throughout the course of their lives. I mean, forget where you put your keys, the remote. If you ever watch the show Darwin Awards, some quite terminal errors people make. You didn't look both ways, while crossing the street or something like that. And then things that are sort of closer to this kind of stuff I think about, which Hume calls the magical powers of the soul, when he's talking about aggregating the relevant information in making a decision. And I think the answer that Jobst had given previously is that even with this sort of primal intelligence, it may still be quite hard to model. But we're here, right? We're here doing it quite easily, I think, in many instances. So I just wanted to go back to this idea about there being certain frequency of occurrence counters in the mind that register information automatically without it being the focus of our attention, thereby saving a lot of mental energy. Not so much heuristics in the way that Professor Smith was talking about it earlier, but that there are certain genetic endowments, and we're getting sort of clear about how these actually work in such a way that we can treat them piecemeal in building out an intelligent system, right? And insofar as we can do that, the problem doesn't seem as complex as an n-body problem now, right?
Okay, so let me have a go. First of all, I didn't say that language is mostly innate. On the contrary, I think that there's a huge amount of learned features of language that we acquire in the process of language learning. A lot of it is innate, but a lot of it is not innate. And I think I agree with most of what you were saying. It's just I would put a different tilt on it. So one of the analogies that we provide in the book goes something like this. You have a river delta, let's say, and you have sticks which are flowing down the river, and then they're going off in different directions through the delta, and sometimes they're joining up with other things, so bits of debris attached to the sticks and so forth. And you get very, very complicated outcomes as they flow out into the sea. Well, that's the way the brain works. The brain is a kind of river delta, and there are things flowing through it, and they take certain pathways because of other things which are going on within the brain. And it's not a process of calculation. It's not a rational process. It's a natural biological process. But because we are endowed with language, we see lots of rationality in it. We see the logic of the language. But when we are reacting to the world, making decisions and enjoying things, we're not calculating. The brain is not like a computer in any way. It's more like a river delta with lots of debris and molecules flowing through it and so forth and so on. And you can't model what happens in a river delta.
The point is,
you better
I don't think
say something sensible now.
The point I would like to make is that you cannot, so whatever should be able to run in a computer must be a mathematical model, right? So if you want to execute something in a Turing machine, then you have to be able to create a mathematical model that runs in the Turing machine. And actually, not all mathematical models can run in Turing machines because there are many mathematical problems that are not Turing computable. So only a subset of mathematical models can run in a Turing machine. And those, what we show in the book is basically that you cannot construct intelligence by putting simple algorithms together to create more and more complicated ones. Because what you do when you do this, you are doing compositional AI, which is basically what my company does. And it's something very useful, but you can only use it to solve special problems. And when you do this properly, these special solutions can be much more powerful than a human being. So computer will beat a human being in chess, now in Go. And actually, in our case, we are beating human claims managers in determining and in evaluating insurance claims for car repair. Yeah, it's a big problem, and our machine now outperforms the human evaluation of a car repair bill that's handed in by a workshop to the insurance for payment, and this is so you can solve special problems much better than the human brain can, because you can avoid the mistakes. You can create series of equations that work together to avoid all these mistakes and so on. But that has nothing to do with intelligence. It's just writing down a recipe for a Turing machine, very much like Charles Babbage wrote the first programs for Ada Lovelace for the, what was it called, Barry, this machine they had? The first computer?
Something engine.
Yeah.
Analytical engine, I believe.
Yes, thank you, the analytical engine. And basically what we still do this now, with the difference that of course the Turing machines we have nowadays are much more powerful than the analytical engine of Charles Babbage, and that of course also the programs we can write, the models we can make have many more variables, but it's still just a prescriptive solution that we give to the machine that it can repeat and repeat, and it has actually nothing to do with intelligence at all.
Okay, good. Thank you.
Thank you.
I think I will ask a question at this point because there's no one else who has a hand up right now, so I guess I will go ahead. I, like Harjeet, was wondering what happened around slide 50 when we were, I guess what we're trying to argue is roughly in outline like this. Human minds are complex systems can't be duplicated, or I don't need to look at the details here exactly, because I'm going to give a very, I thought that the argument that human minds are complex systems went by a little fast. I thought it went something like this. It's made up of trillions of atoms and molecules, and each of which can have an effect on what happens in a human brain or mind. But I guess I was thinking, well, let's consider an analogy. This is my simple-minded analogy. Suppose we imagine some people in the, let's say, 13th century, some human beings in the 13th century who encounter a watch. Of course, watches are made up of trillions of molecules, and how each molecule behaves can have some effect on the watch. Nonetheless, one can make watches. They could, by looking at it, and they may, if they have enough mathematics, even be able to just be able to explain and predict how it works. But in any case, they may be able to duplicate the watch, perhaps using very different materials, and maybe they'll eventually, instead of having it run on a spring, they'll add in quartz, but it'll still be a watch. So I guess what I'm getting at here, and of course this could happen with similar things. We can imagine ourselves encountering a bit of alien technology on our front yards, and we may be able to take it apart and figure out how it works. Although, of course, that alien technology, how it works, would depend on the trillions of molecules that make it up.
So there's
so
a very
let me just
Sorry.
The question is, so clearly, first of all, one, do we have to be able to have a model of how all the trillions of molecules work in an object in order to, let's say, explain what's going on and duplicate what it does, perhaps using different materials? I think not. So, and I hope that Barry's argument did not depend on some sort of assumption like that. So I guess I would want to know, I assume that Barry's argument didn't rely on such a premise like that, but if not, then how exactly did it go?
You want to do this, Jost?
I would, yeah, so it's quite easy. So the machines you're describing, they are non-complex systems.
Good. Now, good. So now what I need is an argument to the conclusion that brains are complex systems, and not merely from the premise that they have trillions of molecules in them.
So the number of molecules is not at all the criterion for system complexity. So the watch is a non-complex system in which the fundamental laws of physics are the fundamental interactions of physics. There are four of them. Are acting in a way that allows a perfect mathematical description of the functioning of the watch with quite simple equations. And so it's not a complex system, but it's actually a simple system. And such simple systems are all the machines we have, including computers, are simple systems in that way that they can be described by mathematical models perfectly, and that they can, unless they break out of usage or lack of maintenance, that they continue to work according to these equations, no matter how many molecules they have. Even a quantum computer is actually such a simple system. And complex systems, they are, the difference between simple and complex systems is that complex systems can't be modeled with the inventorium of modeling techniques that are available in physics. And that's because they have properties that distinguish them from the simple systems. And the most important of these properties is the energy flow through those systems and the dissipation of energy. And whenever systems are dissipative and non-ergodic, then you cannot, and they have other properties like evolutionary properties, they can create novel element types and so on. And whenever they have these properties, it becomes impossible to model them with equations, and that's independent of the number of molecules. So again, amoeba is just one cell.
Say, hold on, what was that last bit? A what?
An amoeba.
An amoeba. And I'm sorry, I'm
Yeah,
sorry.
It's just, no, it's my bad English.
No, that's my problem. Sorry.
Is already very complex system. And so that's the point. It's not the number of molecules, but the way they interact and the way they can change and the way that energy moves through such an object that makes it a complex system.
So
that's the core argument.
I take it systems that involve turbulence are also going to be complex. I take it. I'm bringing that up because if it is the case, then it seems that we can duplicate systems that involve turbulence. I mean, just to some satisfactory degree, we can create some of our, I take it, some of our systems depend on, our technology depends on creating fluids with a certain amount of turbulence. We design aircraft that can take advantage of turbulence, although we may not have an exact mathematics, etc. So, so it could be the case, couldn't it, that we have a system for which we can't give a huge, perhaps as precise a predictive theory as we can for watches, but that doesn't seem like it's always a bar for duplicating or whatever functions we want from that object. So we could do the same for brain and get a non-organic brain just that we construct on similar.
So first of all, to get to your turbulence example, turbulence is non-repeatable. So if you create exact conditions, for example, of a stream of water that's flowing into a pool, and you color some of the molecules in the water, and then you can follow how they flow into the water and how they turbulently behave, and you repeat the experiment, you can never get the same pattern of movement of the molecules in this turbulent flow. So turbulence is not repeatable. What you were referring to in aircraft building is buoyancy, Auftrieb.
Okay.
Buoyancy.
So my example was bad, but
no, it's not a bad example. It just shows that the part of nature that we can master with physics is actually the part that is usually inanimate. Yeah, there are some examples with animate systems that they are usually inanimate, and for the part that we can master and reproduce, we need very simple laws that apply and that are so powerful in dominating the scenery in which we are intervening with our technology, that the chaotic or complex aspects play no role for what we want to achieve. So for example, for flying with an airplane, there are many complex phenomena that happen while the airplane is flying, but they are not relevant for our ability to manipulate material to make a flying object. And so basically there is no way and no single example where we can actually reproduce the behavior of complex systems by mathematical modeling. There's no single example. So all the examples
but maybe I guess what I was saying is I'm still trying to get to the conclusion that brains are complex systems in your particular sense. I mean, it's clear that in some very ordinary sense of the term complex systems, they are complex, but you've got a particular notion in mind, and I'm still not getting the premises that will enable me to deduce. You know, I take it we're trying to get a proof here, so we'd have to have some very strong premises, it seems. Not just, for instance, that they are big and that they can be, their behavior can be influenced by all sorts of impinging energy, because that's true for lots of things, that I would think.
Yeah, there are of course physical criteria that define complex systems exactly, and they need to be fulfilled to be complex systems. So in this talk, Barry didn't list the properties that define complex systems, but if you would look at this list and I could read it out for you, or show it to you via screen sharing, you would see that all of them apply to the human brain.
Okay.
So
I will
it's
send
very
him
well
the
defined in
relevant
physics.
sections. I'll send him the relevant pages.
Yeah. But so the notion of complex
So
systems.
in any case, we need a very complicated argument to get to the conclusion that some object is a complex system in your sense. We shouldn't take it as obvious just looking at the brain that it's a complex system in this sense.
Actually, the argument is not so hard. It's an argument from thermodynamics, from statistical mechanics. And in statistical mechanics, it has been recognized in the 1910s, 1920s, what a complex, and then developed much more in the 1950s, what a complex system is. And there are lists of these properties. And when you know these lists, it's quite easy to check which objects in nature, animate and inanimate entities, are complex and which are not. Okay. So it's not that complicated if you know the thermodynamics or statistical mechanics definition of complex system.
We have somebody else asking a question now. Lewis, anybody else who has a question? I'll continue this for about 5 or 10 more minutes. Go ahead,
David,
Lewis.
I'm going to move physically, but I'll still be able to hear and speak.
Okay.
Yeah, so this is just following up on what the exchange that was just happening with David Brown. So I guess, and it ties back into my question from earlier, but since it was doing that, I wanted to jump back in. So I guess what I'm trying to figure out though is, and this will be one of the points where Barry, I think, doesn't agree with Aristotle, who thought the brain was largely doing refrigeration work for the body. Like the brain may be thermodynamically complex, but this is where it seems like it matters for us to figure out how much of what the brain is doing would need to be simulated by a computer in order for the computer to be simulating intelligence, or, effectively being intelligent, right? And maybe I guess this ties in with Neil's question as well, because if the computer, if the computer can simulate a non-complex subset of what the brain is doing, then even if the brain on the whole is complex, there might be a non-complex system that can abstract a portion of what the brain is doing and still do a yeoman's job of being intelligent. And so that's really the heart of what my first question was, is why, if I was already sympathetic to the idea that I'm not that smart in the first place, why was I supposed to think that all of the thermodynamic complexity of the brain is needed for the smartness? So that that's like, yes, the environment is super rich, and yes, my brain is doing lots of stuff, but not everything my brain is doing is smartness. Like, some of what my brain is doing is making sure that my heart beats, but like, not all of the heart beating is relevant to writing a paper. Not all of the heart beating is relevant to all of the intelligence stuff that I'm doing. So maybe this is tied into the part where you guys are anti-multiple realizability, like Harjeet was asking about. But like, unless we're super duper holists about the entire system of me, it seems like we'd need something to connect me from the whole brain system is thermodynamically complex to any particular subset of the things my brain is doing can't be simulated by a non-complex system.
Of course. So Barry, maybe you want to start.
No, you take this one.
So of course there are many functions that our brain can perform that are non-complex and then that can be actually better done by an algorithm, like searching. Now, searching is something, at least searching in a very well-defined way, can be done much better by a machine, and that's basically why human chess players can be beaten, because chess can be formulated as a search problem. So I agree that there are some traits of what humans can do that machines can do much better, especially counting, which is the basic function. Also remembering. So if you manage to take a part of a memory and put it into a digitally storable format, then you can of course have much bigger memory than human brain can have, and so on. However, none of this has to do with intelligence. All of these are aspects and capabilities of the human brain that the computer can do better than the human. But because of this, the computer will not be able to solve open problems. And I think that's so to solve a problem that it has never encountered before in a new situation. That's the core of Schroeder's definition of intelligence. And this cannot be, we don't know where this skill comes from, but we know that we cannot obtain by composition, neither by implicit learning, like what the neural networks do, because all these attempts to simulate intelligence only lead to very special situation-specific solutions, which can be very powerful. So I agree with you, but it has nothing to do with intelligence. So there's no layered model of intelligence, right? There are many capabilities in the human brain that we can somehow emulate with the computer, but we are not getting to intelligence by doing this. That's my answer to this. And it has nothing to do with smartness or how high the IQ or low it is. It's just that this ability to react spontaneously to new situations and solve them, we don't know how it works, and we have no compositional model for it, and no layers, and no non-complex. What also another very important aspect is that simple systems have very, very simple equations. So even for example, the quantum theory, the equations from quantum theory are quite simple equations. Yeah. So they have not many variables, and even the general theory of relativity there are not many variables used to formulate the general theory of relativity. So the simple problems, the non-complex problems that we have mathematical models for that work are really simple in a way. And so so if you know these models and look at them and what they can do, they're amazing, but they are just off the mark for intelligence.
David, you're muted. David Brown, you're muted, and David Gray typed a question in the chat.
I'm sorry. I'm sorry. I didn't realize. Okay. I think I see that David Gray wrote something in the chat here, but I don't know. Go ahead, David Gray. David Gray, do you want to ask your question now? Oh, you're okay. So I'll read it out for Barry and Yops. From David Gray. My microphone isn't working, but when I play chess, am I engaging in intelligent behavior? But when a computer plays chess, it is not intelligent behavior?
That's
so
right.
Can I take this one?
Yes.
Maybe so, although Yops already said yes.
So I mentioned at one point in the talk that the notion of artificial general intelligence. We've been talking about intelligence. There is narrow artificial intelligence. That's a technical term, which is illustrated in things like pattern recognition, facial recognition, chess playing, and so forth. And AI can be very powerful along these narrow lanes, more powerful in many cases than human beings. But what we do not have is impressive examples of artificial general intelligence, which is the kind of intelligence that is manifested when human beings, for instance, make positive contributions to philosophical discussions about artificial intelligence, or invent something, or prove a new mathematical theorem, or create a new kind of music. That kind of general intelligence is something that the computer has thus far been unable to simulate, even in spite of all the efforts. And we think there's a reason why it's been unable to simulate it, because it's impossible.
I think the question about chess is great, because it puts into very simple terms what we're trying to say. When a human being plays chess, the human being indeed uses his general intelligence to play chess. But when a computer plays chess, it's applying a huge set of rules which was designed to simulate it playing chess. But it doesn't think. It's just calculating through all the possibilities at each move. Actually, not all of them, because there are some heuristical tricks to reduce the search space. And then it gives a score to the move that has the highest likelihood of ending the game by winning it. And that way it progresses in a completely deterministic manner to play chess, but it does nothing intelligent. It's just following a strict recipe. And so therefore, it's a very good example that shows, while the human actually solves the process, the game of chess in a very, very different way. And I think it's a very good example. And Barry, if you, David, if you allow us to use it, we'll use it in the book. I think we should put it into the book, because the manuscript is still with the publisher, so we have still a chance to insert it. It's a great idea. Thank you very much.
I think at this point we should thank our Barry for his talk, and I think maybe Jops too, since he absolutely contributed a lot to the discussion. So thank you all, and
thank you all.
Thank our speakers, please. All right.
I can hear the applause. It's overwhelming.
Thank you.
All right. Thanks very much. See you at the next talk, which I think is 2 weeks from today.
Very good. Thank you, David.
Thank you.
Bye-bye.
Bye.